Okay, good evening, guys. Today we are going to talk about Hermitian Operator, a very important topic in quantum mechanics for the BSc syllabus. Uh, you might have I already took a class in my regular class that what is about Hermitian Operator. We know that Hermitian operators always produce real eigenvalues, and as far as quantum mechanics goes, all the operator that we use in quantum mechanics must be a Hermitian operator, and we know about the condition. Today we'll just try to understand what is exactly the Hermitian operator is. uh, you might know this, you might have seen the kind of this thing, huh? Suppose psi1 star a cap psi2 d tau is equals to, we know if the a cap means if the a is a Hermitian operator, then this must have equal to a cap star psi1 star psi2 d tau. So I'm writing just a generalized type of equation for that. So if A is a Hermitian operator, then it must have to satisfy this condition. So today we'll try to see and understand how this condition arrives. Now, for example, let us talk about a free particle. We all know about free particle. What's a free particle? The particle upon whom there is no external force is acting, or if we say V is equal to 0, because we know that if V is equals to 0, that means the potential energy is 0, then there is no force acting, because whenever there is a force, there will be a corresponding potential energy, no matter it is electrostatic potential or gravitational potential, or in case of Hooke's law, the spring force. Okay, so whenever restoring force, so whenever there is a potential, there is a force. But for kinetic energy, you don't need force, because you simply need velocity. You don't need acceleration there, and the velocity half mv square will give you kinetic energy. So we know about that. We have talked about that in our regular classes in DR college, that if potential is 0, that means there is no force acting on the particle. So those kind of particles are known as free particle. So we have talked about a one-dimensional box where a particle is left inside a well, and we put the particle inside a boundary such that if this is the boundary, the particle is here, and the potential outside is infinity, this side is infinity, both sides infinity. That means the particle has to wander here and cannot go beyond this. So if I say it's a free particle, then what will be the Hamiltonian operator for this? We know Hamiltonian operator. We know about Hamiltonian operator, which is H, the energy operator, total energy operator, which I can write minus h cross square twice m d2 by dx2, which is the kinetic energy part plus the potential energy part. So let us talk about free particle in one-dimensional box. So if I'm talking about free particle, that means I can rub this as 0. So let us consider this operator, minus x cross square by twice m d2 by dx2, 2 dx2. Let us talk about this operator. Okay. This is the operator we are talking here about. H cap is equal to minus h cross square by twice m d2 dx2. Let fx and gx are two functions. These two functions are such that at the boundary, means x equal to 0 and x equal to a, at the boundary both the functions vanish. They are very much similar to what is your wave function. In one-dimensional box, you know the wave function vanish at the boundaries, isn't it? So this is very much like your wave function. Now, so we have fx and gx, two functions which will vanish at the boundary x equal to 0 and x equals to a. Okay, so let us write this. Let us try what happens to this. We have fx, then we have H operator, Hamiltonian operator, then we have gx. Let us see what happens to this. And the integration is there, dx we have. Okay, integration in the box, whole box, so you will have a 0 to a. Let us see what happens to this. So here we can talk about, we can take, suppose we can put the value of h cap here, no? H cap value is minus h cross square by twice m d2 dx2. So take the minus h cross square by twice m outside, you have integration 0a fx h cap gx dx. H cap means your d2 dx2, means double differentiation of whatever function on the right hand side. That means you can write, if d2 dx2 works on gx, it will produce g double x, yeah, g double x means double differentiation. So that's what written here, fx g double x x dx. Now let us see what we can do with this. Fx, make fx as the first function and g double x x as the second function, and we are integrating this thing under the limit 0 to a. So it's kind of product of two functions, u and v, first function, second function. So first we'll get this. I've written first this. Okay, no problem with that. First we'll get this fx and g double x. The integration of g double x will be g dx x. We got this, and the second part of the integration will get this. Okay, yeah. Now in this part, if x tends to 0 or a, means the boundary, at the boundary the function fx and gx both will vanish. That means they will become 0, like wave function, no? That means at the boundary, suppose the fx becomes 0, anything multiplied with 0 is 0, so this will become 0. The first term will remain. Now again you see here, you have f dash s and g dash x. Again you consider f dash x your one function and g dash is your another function. Again product of two function. Again you will do integration. So what we'll get here? Yeah, again you will do the integration of f dash gx. We have f dash x g dash x, no? So again if you do integration, this time you will get what? You will get, let us try here. Let us see here. What we'll get? It will become f double x x. Outside is minus, will again it will become minus 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 plus integration, and this will become gx, and you have dx. Integration 0 to a. Okay, that means we started with fx g double x x, and now you are getting f double x x or f double prime x and gx dx. Or in place of f double prime, I can write like this, no? Gx d2 dx2 again gx, isn't it? So, or the minus h cross square by twice m is waiting outside. I can bring it here so that I can write like this, fx, sorry, integration 0 to a. I can get, let's try to write it here, integration 0 to a gx f, sorry, h cap fx dx. So you started with this fx h cap gx, ultimately you got gx h cap fx, the function inverse, changed. That means you got this fx, you started with this, you got this. Okay, similarly for complex function we can have, if suppose f and g both are complex function, then we can have, if you start with f star x h cap g etc. yourself, you will end up like this, a star is there. Okay, or in mathematical terminology we can write, suppose f star a cap g t tau integration will be equal to integration g star a cap f whole thing is star. If I break this whole star term, sorry, okay, if I break this whole star term, then I will get like this. Suppose this star is here, no? So it will become, if I break this star, this bracket, I will get g star star means g x h cap star, and you have f star x. You had here f star x h cap gx. Ultimately you get gx h cap star f star x. Now if you replace f by psi 1 and g by psi 2, you will get psi 1 star h cap psi 2 will be equal to psi 2 h cap star psi 1 star, which is the condition in the Hermitian operator. So hence the condition in Hermitian operator is proved. So I tried with Hamiltonian operator in case of a one-dimensional box. You can try yourself for the momentum operator as well. And interestingly, it will in case of momentum operator also you'll get the same thing. You try yourself, and remember, you have in momentum operator you have a term I. So when you differentiate, when you get the p star, and then you need to get p star, no? So you in place of I, the momentum operator is like this, no? Minus I h cross ddx. So if I want to take the p star, means conjugate of the momentum operator, it should be coming like I h cross ddx. So the minus term will gone. So if you try yourself, you will see that this minus term will go by itself. How? Because when you do the first integration, the minus term will be there, and since momentum operator is a first order differential equation, first order differentiation, so it's not equation, first order differentiation, so you will get the additional minus there, so that will work for that conjugate of the momentum operator. You try yourself, you get the result. If you don't, you put your comment there. I will do it for the momentum operator as well. Okay.